So this is the interface for the measurement from the bearing that's deliberately been damaged. And this time, whereas previously we were seeing data all the time, now we only get data if we hit the restart spectral averaging button up here, and we're going to take 5 averages, which is specified here. You can see again I've got those cursors, fundamental, first harmonic, second harmonic down here, and these are automatically calculated based on the position of this fundamental cursor. When I hit the run button, the measured shaft frequency here from the shaft at the end of the belt drive is automatically calculated, and these calculated bearing frequencies are derived from the sheet that I showed previously in the settings tab here, based on that shaft frequency 19.86 Hertz. And so here you can see, if I restart spectral averaging, this is the time domain signal which is coming in from the accelerometer, and as I increase the load on that accelerometer, you'll see that we clearly get much larger peaks. Note that the scale is changing here. It's finished averaging now, so we are no longer collecting data. But if I restart averaging now, you can see that some of these excursions are all the way up to 1 volt. So there's some big accelerations here now that I've increased that voltage. And also you can see now that there are some peaks in the spectrum that are as a result of the fact that I've got damage to the bearing itself. Okay, whereas these weren't here when the bearing was unloaded. Now, because we've applied an axial load, we actually get much higher peaks in this frequency spectrum. There is some fluctuation in the frequency. We're not getting perfect control over the shaft speed, but if we are able to maintain that shaft speed pretty constantly, you can see that these peaks appear in the spectrum. You can hear it wandering slightly up and down. This shaft speed varies slightly. It's pretty hard to maintain that shaft speed, and that clearly leads to problems in our average spectrum, because we have a peak at one speed in one spectrum averaged with a spectrum that contains a peak at a slightly different position. But if we get a good constant shaft speed run, then hopefully we can see, if I move this cursor now to this peak, for example, this is at 78.8 Hertz, and that's pretty close to this BPFO frequency here, 76.74, which has been determined from the speed multiplied by this function, and it tells me that there is a damage, or that bearing is exhibiting damage that's associated with a problem in the outer shaft, the outer cage. Similarly, there's a high peak at around about 98.6 Hertz. Some of these peaks occur at fundamentals of the shaft speed. So here's the fundamental frequency, 20 Hertz. It's a very tricky thing to be able to interpret this spectrum, especially with that varying speed, and to be able to fully understand why all of these peaks originate. Sometimes they are the second and third harmonics, the first and second harmonics of these individual frequencies, and that's why we include this table here, where based on the shaft speed it's possible to determine the cage fundamental frequency and the outer race frequency, the inner race frequency, and the ball spin frequency, and then we can multiply those by by 2 and 3 to get the first and second harmonics of those. And we're looking for peaks in this spectrum associated with all of the frequencies within this table. You want to be able to also determine the recording length time, the FFT for the frequency resolution, the sample rate, and the maximum frequency output from the FFT, and you can see that here. We've got 2 seconds, and some of the other information that you need is captured within here. I'm not going to tell you everything, but from 2 seconds of recording time length you can calculate the frequency resolution, and for a sample rate of this you can determine the maximum frequency output that we observe in the frequency spectrum. That's the end of this video series on machine vibration condition monitoring. Thank you.